Hello everyone. So last time we did, we saw the differentiator. It was an amplifier that could differentiate instead of just doing any kind of arithmetic operation. And this time, I think it should be fairly obvious. Going to see an amplifier that's going to integrate. That's going to integrate any given voltage signal. So the diagram again is actually derived from our inverting amplifier. Okay, surprisingly, it's being very common here. Okay, let's see. But again, there's one change. Let's see. It's not here. You have your resistor here. Okay, and this circuit. Another thing about this is I'll draw it in a way that you'll see in most op-amp problems which don't involve like summing op-amps. Uh, it's drawn something like this. They don't draw your ground explicitly. They don't mark this as the ground. Instead, instead of saying V1 is this potential, instead it's the voltage between these two terminals. It's really the same thing as we did before. There's really no difference in functionality, just a different way of drawing this. So we have this is our negative, this is our positive, this is our output, and we have something here that's not going to be a resistor. Okay, and you might have guessed, well, for those who are guessing this is an inductor, that's what I guessed at the first time too, but actually this is a capacitor here. Okay, so we have a capacitor here. Okay, looks a bit weird like this. Anyway, so we have a capacitor here. This is our V output, and again, this is drawn like this. Yeah, actually, let's see. Okay, so it's actually usually drawn like this. You have your other terminal here, and V output is the voltage difference or the potential here. Sorry, the potential difference here. Anyways, so that's your circuit. This is gonna be your capacitance C. Okay, this is gonna be your capacitance C. Okay, and this is a resistor. This is some resistor called that R. So this is how your integrator looks. But again, we didn't prove that it integrates or even does anything meaningful. So let's actually try to prove that. First thing, let's mark this as the ground. Okay, like the very basics of nodal analysis. Let's mark this as the ground, which usually we just it's just included in the diagram, like in the cases before. So if this is the ground, this is going to be 0 volts. And well, since this is an ideal op amp, this also has to be 0 volts, right? Okay, and also the current here has to be zero. The current here has to be zero. I'll write a small zero here. Okay. So and there's let's say there's a current here. Okay, current entering this node like this through the capacitor, and there's a current that's exiting. The current that's exiting through this resistor. Okay. So let's see. This is your V output. This is your V output. This is zero. Okay. Well, first thing, if I call this I sub R, if I call this, whoops, no, opposite. This is I sub C. Let's call this I sub R. Okay. So your I sub C is gonna be equal to your I sub R plus 0. Well, the 0 would just disappear. So the current entering is the current exiting, basically just using KCL here. So I sub C equals I sub R. Well, what is I sub C? And again, you might notice why the current direction I took here, it's the opposite of what I've been doing in the previous videos. There's a very there's a reason, just to make things simpler on my head, to be honest. It's because the polarity of the potential difference or the voltage here, it's something like this. So you have V output and goes to 0. So it's something like plus V output and 0 and minus. Okay, so this is the direction of the polarity, and that's why I took the current in the same direction. Okay, so that I don't have to include any negatives in the capacitor current formula. So the capacitor current is going to be my capacitance multiplied by the derivative of whatever voltage is across this capacitor. Okay, so it's V output, so derivative of V output. Now this is gonna equal my current through this resistor. So the potential difference in this direction is 0 minus V1, right? 0 minus V1. Okay, so 0 minus V1. Okay, the potential here is in fact V1, because this is the ground, this is V, and so this is up to V1. So 0 minus V1 divided by R. Okay, so we're yeah, okay, so I labeled that V1, right? Anyway, so you could call it V supply, V1. I guess for now I'll actually stick to V1, to be honest, because I will actually see the summing integrator. So I'll actually not change that for now. So this gives us, let's see, derivative of the output voltage is equal to negative 1 by RC multiplied by V1. Okay, but this is the derivative of the output voltage. You actually just want the output voltage, not its derivative. So to that, to find that, we need to integrate both sides. So V output is gonna be equal to the integral of this side, but this is just a constant minus 1 by RC, so we can pull that out. From the integral, and what's inside the integral. And actually, this is, well, the big question is what type of integral are we taking? And usually, we're gonna assume that the output voltage is 0 when time is equal to 0. Okay, the output voltage is 0. The output voltage is, wait, I shouldn't have chosen red. Let's choose a different color. So this is 0 when t equals 0. T equals 0. This is usually the assumption that's made, and if you make that assumption, you can actually take the if you take the definite integral of both sides. Okay, if you take the definite integral of both sides, you'll have from 0 to t v1 dt. Same thing here. If you take the definite integral of this side from 0 to t of this, so what you'll get on this side is V output evaluated at t. Well, we can just call that V output minus V output evaluated at 0. Okay, so it's something like V output minus whatever it is evaluated at 0. Wait, so evaluated at t, whatever it is minus whatever it is evaluated at 0. Okay, but we already said we're assuming this to be 0, right? We're assuming this to be 0. That's why this disappears, and we just omit the parameter usually from here. So we just call that V output, just to make the formula make the formula look a bit neater. Anyways, so this is my result. This is the formula for my integrating amplifier. So my output voltage is gonna be equal to negative 1 by RC times the indefinite integral of from 0 to t of your supply voltage. Okay, and one thing, again, this is based on the assumption that your output voltage is in fact 0 when time is equal to 0. If for some reason that's not the case, you'll have to add a constant here. Some constant. Okay, so with all that said and done, let's actually see some problems. Actually, there's one really important thing that I'd like to show you. Well, first thing, again, like the differential, if you want to consider RC as the time, as the time constant, you can, and you can write this formula as V output equals negative 1 by tau 0 to t V1 dt. Okay, but well, I don't know, some you might or might not like the time constant in this context, but I just like to view it as some constant multiplier. So that's why it's kind of intuitive. But anyways, your wish if you want to consider it as the time constant or not here in this context. But anyways, that aside, there's one really important thing about this formula is that does exactly the opposite thing. Okay, exactly the opposite thing as what the differentiator formula does. Okay, and now it might sound obvious because obviously the differentiator formula differentiates and this one it integrates, but there's more to it actually. if you see the differentiator formula, and let's go to that, it differentiates your supply and then it multiplies by negative RC, right? Okay. Um, and so what does this one do? It integrates your, it integrates your supply and then it multiplies by negative 1 by RC. So if for these two circuits, if R and C are the same, obviously the positions are different, but if R and C are the same, these two formula actually do the exactly the opposite thing. Okay, or in other words, you could say they are inverse functions, right? They're inverse functions. That's why whatever signal, suppose say you take a signal from, you take some output from a differentiator. Okay, so you take an output from a differentiator, um, and you pass it to an integrator. You pass it to an integrator. You're actually going to just get your original signal back. Okay, let's see, integrator, and let's see your original signal. Wait, I'll actually draw this. Okay, so suppose say you have some original signal. Okay, you have some original signal. So when you pass it to some, differentiator, and then you pass it to some integrator, whatever output you get, well, you're actually just going to get your original signal back. Going to get your original signal back. Okay, and also likewise, same thing. If you pass some signal to the integrator. Oops, that's not supposed to happen. Let's see. If you pass some signal to the integrator, then and then pass the output to a differentiator, okay, you're actually going to just get your original signal back. Okay, you're gonna get your original signal back. Yeah, the diagram has become a bit confusing. But anyways, just wanted to say that these do exactly the, opposite thing of each other, especially given they have the same RMC. But with that, it actually saves me some time for this video, and that's because we can actually refer to these examples. If you saw the differentiator video, these are, this is one example that we did, where differentiator, you feed the supply voltage or supply signal to the differentiator, and this is the output that you get. Suppose this is your supply signal, so I'll label that. Suppose say this was your supply signal, and you pass this to an integrator with the same resistance, RNC values of RNC as what we used in the problem with the differentiator. Given these, and this being the supply, we're actually going to get this as the output. Okay, this waveform as the output. As I said, the integrator is gonna do the exactly the opposite thing. It's kind of like an inverse function of the differentiator. And so, interestingly, again, just like the differentiator, really interesting that the integrator is also able to change the shape of your waveform, right? So that's pretty cool. It converted this square waveform into this triangular one. Okay, and also there's it should also make sense if we go by the formula. The formula was what? So the output voltage is, again, just like the differentiator, we need to be careful about one thing. It's about this negative sign. Okay, so we do need to be careful about reversing the polarity at the end. Okay, with that said, it should make sense. So basically, you're taking the area from the beginning, from t equals 0 up to your current time. You're taking the area, okay, under the supply voltage curve. You're dividing that by some constant, multiplying or dividing by some constant, and you're making it negative. You're reversing the polarity. So if you just go by this, this should also make sense in that way, because suppose say at this time, okay, at suppose say at this time t. So if suppose say if we want to find the value, okay, of the output voltage here, it's going to be this area, right? This area, uh, divide multiplied by some scaling factor, and also you need to reverse the polarity. So this area, as you can see, is negative, and then it would get scaled up. But importantly, you'd also have the value would be negated, so you have a positive value. Okay, just like here, suppose that this is this one, so you have a positive value here. And as you can see, as you move forward until 2 milliseconds, your area, it's I guess you could say, it's becoming more negative. Increase wouldn't be the right thing to say, I guess. So it's becoming more negative. So as you can see, this is becoming more positive, actually, in a linear way. It's obvious if you do the integration. This is a constant, so this is a linear function at this part. So and then it changes. Now after 2 milliseconds, it's 1. Your supply voltage is constant at 1. Okay, so again, it's like same thing from the beginning. Okay, from t equals 0, you keep adding the area. Okay, you keep adding the area. Suppose say at t equals 4, it might not look like it because how I drew it, but these two areas are exactly the same. They're equal, and also the fact that their signs are opposite. So these two cancel out, and you get a value of 0. Same thing, which is what's shown here. The value of the sub output. So this is going to be the output now. The value of the output voltage when 4 milliseconds is 0. As you can see, it goes down because it was, you built up to an area which is actually negative. Okay, it was negated here. But anyways, you built up a certain area with certain sign, and then you're going the opposite way. Okay, you're taking in positive area, so they're canceling until you reach 0, so it's decreasing. Then the area is going to increase in a positive sense, but that value is negated, so you're going down here. I think you get the idea. Okay, basically you just need to be careful about the negative sign, but other than that, it's basically just keep compounding your area until the current value. And the negative, you should get the idea of the shape of the curve, the output voltage curve. Let's actually try one of these fresh problem. So the curve that I have, it's a sawtooth curve. That if I feed this to an integrator, okay, if I feed this to an integrator, and which has the resistance R. Okay, the resistance R for my integrator is gonna be, let's see, R is 10 kilo ohms. Yeah, and the capacitance is, let's see, it's 0.25. It's 0.25 millifarad. Sorry, not millifarads, microfarads. It's 0.25 microfarads. So if I feed this as the supply voltage to this integrator, what's gonna be my output? Well, first, again, let's draw a set of axes. So let's go back here. Now what happens here? First thing, we need to again be careful with negative sign. Okay. So what happens here? Suppose say, from z at this time, suppose say from 0 we went to this time. Well, this is going to be some area. Okay, so the thing is, what's happening here, you have this part of the curve, this part of the curve. It's linear. It's a linear function. If you take the integral of that, it's going to be some quadratic, so we know it's gonna have the shape of a parabola at least. And the negative area, as time goes on until 1 millisecond, the negative area is increasing. Okay, you're compounding negative area, and if you negate that, you get a positive value. So interesting. You start from 0. You don't have the definite integral. It's going to be 0 when your time is 0, and and then it becomes increasingly positive. Until 1 millisecond. Okay, and in a quadratic fashion, again, say in a parabolic fashion, say. So it's my curve should look something like this. It's gonna be the right side of you know smiley face parabola. So I'll try to draw that. It's gonna look something like this. Okay, I hope that looks good. So until 1 millisecond, right? So until 1 millisecond. All right. So if that's done, now when now let's come to this second branch, you could say. We have covered this, and suppose if we are here. Okay, Okay, so we compounded some negative area, but now we're adding positive area, which is basically canceling that. Okay, and it's until 2 milliseconds. And if you see, this triangle and this triangle, the areas are equal, and the signs are opposite, so they cancel. The areas cancel. So your integral is going to be 0. So what I'm saying is, what I'm trying to say is, your the value of your output voltage, okay, it's going to decrease, okay, because it's the size of your integral is decreasing, the definite integral. It's going to decrease, okay, and also again in a parabolic fashion, because if you again consider this branch, this branch, it's a linear function, right? So if you take the integral of that, it should be a quadratic or a parabola. So let's draw that in. So at 2 milliseconds, it's going to be 0. It's going to go down in a parabolic fashion, okay, the reverse of how it went up. Okay, and at 2 milliseconds it's 0. All right. So I think you try you should be able to see what's gonna happen next. This is basically one cycle, right? And it's actually gonna repeat itself. Uh, it's not necessary that the same pattern would have repeated here, especially because we're taking the integral, but our value actually returned to 0. Again, I'm saying it's not necessary. Obviously, it's in the first place, it's not necessary for our supply voltage to be some periodic function. You could have something like this, to be honest. I'll draw some axis, for example. So you could have a trapezium, and then a rectangle, and then some triangle. This could be your supply signal. And if you have something like this, you're gonna have to manually integrate every part, write your output voltage as a piecewise function. uh, it doesn't necessarily, I'm not saying that your uh, output voltage or supply, it always has to be periodic or has to follow a certain pattern, but here it does, okay, because this is periodic, and also the value after one period actually returns to 0 of the output voltage. That's why this same part is actually going to repeat itself. The same part is actually gonna repeat itself, and I'll draw that nicely, because this is continuous. Okay. So this is 3, this is 4. All right. So we actually were able to, just thinking about how, the integral area and all, we were able to find the shape, okay, but we still don't know, what's you could say, what's the value here, what's the maximum value here. All right. To find that, let's consider this portion, okay, until 1 millisecond. Okay, let's use our formula. At 1 millisecond, what should the output be? 1 millisecond. Let's try to find that out. Let's see. um where is it? So this is my formula. So v output is gonna equal at 1 millisecond, negative 1 by RC. So R is 10 kiloohms. I can write it as 10 times 10 to the 3, or 10 to the 4, I guess, times 0.25 millifarad. That's C, your capacitance. 0.25 times 10 to the minus 6. Okay. Integral of, and actually, yeah, integral from 0 to 1 millisecond of this part, right? I could do the integral, okay, but since we just need the value, and to be honest, it's a triangle, so I think you get the idea. You can just easily, it's the area of a triangle formula. So let's see, half into base, which is 1 millisecond, okay, 10 to the minus 3, and height, which is 5, but we need to consider this negative. So negative 5. So let's see, half. That's gonna be half. I'll use a different color. Half into 10 to the minus 3. Oops. 10 to the minus 3 into negative 5. Negative 5. All right. So let's simplify this. If we do, let's see. First thing, um, you'll have a 10 left over. If you cancel this, and if you cancel this, let's see, you're gonna have a 10 left over here. You can 10 left over here. This is 2.5, 2.5, and here you have a negative 2.5. Also, this here you have a negative, so the negatives cancel out. So 2.5 by 2.5, that's actually going to be 1. Okay, it's actually going to be 1 volt. All right, so that should be my maximum value here. That should be my maximum value. This value is 1 volt, so it's gonna peak at 1 volts. Every odd second, you could say. So this is my output voltage. This is the graph of my output voltage, and it should appear very fascinating to you because you have your sawtooth voltage curve. You pass this signal on to an integrator. You just feed it to an integrator with these values, and then you get a very different curve. You get a very different curve, and again, your arithmetic, the amplifiers which just do arithmetic operations, they're not exactly able to do something like this. Okay, so really fascinating. Let's actually just do one problem, not involving graphs. Okay, just hardcore mathematics, you could say. I'm just gonna do this for the sake of doing it, you could say. So our supply voltage is 10 cosine 2t millivolts. Okay, our resistance is 3 mega ohms. Wait, sorry, no, our resistance is, yeah, I'll write that down. Actually, it is written as 3 mega ohms, but I don't want to do that. Let's see, our resistance is, let's see, 3 that's 30 kilo ohms. Also 30 kilo ohms, and our our capacitance is 2. Yeah. Capacitance is 2 microfarads. 2 So what we need to do again is just find the output. It's just find the output, the function, the output voltage function. This is going to equal negative 1 by R into C. Wait, I'll just substitute in the value. So let's see. 1 by R into C. So 30 times 10 to the 4. 3 times 10 to the 4, actually. 30 times 10 to the 3. Anyways, 3 times 10 to the 4. 2 times 10 to the minus 6. 2 times 10 to the minus 6. Let's see. Then we have the integral. The integral from 0 to t. Integral from 0 to t of the supply, which is 10 cosine of, 10 cosine of 2t millivolts. 10 cosine of 2t millivolts. Let's see. 10 cosine of 2t, and gotta be careful, this is in millivolts. Actually, yeah, you're multiplying by 10 to the minus 3. Actually, just make this 10 to the minus 2. That seems more convenient. So dt. All right. So let's see. Yeah, so looks good. Let's continue. Let's see, here you're gonna have 6 times 10 to the minus 2, and here you have a 10 to the minus 2, so these cancel, so you have a negative 1 by 6. Okay, here, you have cosine of 2t. You have cosine of 2t. This was cancelled out. You have cosine of 2t. Take the integral of that, you get negative half sine of 2t. Negative half sine of 2t. Oops. Oh, wait a second. Yeah, slight confusion. It's not negative. I'll erase the whole thing. So half, half, half sine of 2t. Half sine of 2t. Okay, and this is from your time t equals 0 to time t equals t. Okay. So if I take the integral, if I evaluate this here, this is negative 1 by 12. This is negative 1 by 12. Okay. Sine of 2t, it's evaluated at t minus, sine of 0 is 0. So sine of 2t, sine of 2t. So this is my, and this is gonna be in volts. Okay, this is gonna be in volts. So this is my output. This is basically my output voltage. Pretty fascinating. Pretty fascinating. See. So that one's done. let's actually do one problem. And actually, before doing that, I'd like to discuss. If you watch the previous video, you might have a hint about what I'm going to do. This is, our integrator basically came from our inverting amplifier, right? Well, if that's the case, we should actually be able to make summing version of it, the same as we did with the differentiator. And that's true. Actually, it's true. If you just add more branches to this, okay. If you just add in another branch, I can't write here like that. Let's try it here. So if you add in another branch, so this is V1, let's say this is V2, let's say this is not V output, V3. Okay. So, and you have your resistance. Now you're gonna have to name them one by R. You have R1, you have R2, you have R3. Okay. These are connected. These are connected to your inverting input. These are connected to your inverting input. And you have a positive here. You have your output. You have your capacitance linked over here. It's still just one capacitance. You just increase the branches there and on the supply side, and you have let's see, your this is connected to, see, yeah, this is connected to there, another terminal, and you have your ground. Okay. Okay, so this is the diagram. This is the diagram, and you should be able to prove it to yourself, that this actually does to it's summing integrator actually. Well, I'll still just discuss this. So, when we work this out, it's pretty similar to the proofs that we did before for the summing, any summing amplifier. So you have this, and you have this as the single current that's exiting here. But when you add more branches, everything else is unchanged, except that you have more currents, right? So, you have negative, you have, 0 minus V2 by R2. So this is R1. You also have, V2 by R2. And you have negative V3 by R3. Okay. So, and then your formula just becomes, let's see, I'll write this here. So your formula is gonna be V output equals negative 1 over C. Okay, this is the constant factor outside. This is gonna be unchanged. This is one capacitor, and inside what you're gonna have is, it's the weighted integrals. Okay, the weighted integrals of your resistance, of your supply voltages. So it's something like this: V1 dt plus, oops, it's weighted 1 by R2, uh, 0 to T of V2 dt. I think we should be pretty familiar with the summing amplifiers and all about them until now. And this isn't really any novel formula to memorize, to be honest, because it's just a superposition, okay, or sum of multiples, integrators, okay, multiple integrators. That's how you basically get this summing integrator. It's nothing special. Just a superposition of multiple integrators. So that's basically your summing integrator. All right. So let's actually try to do a very simple design problem with this. So suppose, say, you have three voltage signals. Okay, you have three voltage signals. It's V1, V2, and V3, and I want to get this as an output. Okay, somehow I want to get this as an output: 0 to T, uh, V1 plus. By the way, some of these problems are taken from Fundamentals of Electric Circuits, written by Charles Alexander and Sadiku. So yeah, that's the acknowledgement covered. Not all though. Let's see. This is the output that I require. Okay, somehow I need to get this. Okay, somehow I need to get this. I have three voltage, I have three voltage supply signals, V1, V2, and V3. Somehow I want to get this as the output, this kind of Well, since I already discussed, since I just discussed summing and integrated, it should be obvious. But it should also be obvious just from looking at this. You have integrals. You actually have multiple. You're integrating multiple voltage signals. Okay. So one thing, you definitely need an integrator, and since you're adding them, summing them, you need a summing integrator. Okay. So first thing is, I'd actually like to, the integrals are separated here. Okay. They're weighted integrals. So I'll actually like to separate these two. So I'll say I'll still keep the negative outside. So let's see. Uh, 0 to t, 0 to t, v1 dt, okay, plus 4, 0 to t, v2 dt, plus 10, plus 10, 0 to t, v3 dt. All right. So this is just that rearranged. And well, if that's the case, let's actually write out, let's write what our formula would be, for the general formula for the, with, if you're using the summing integrator with three branches, that's gonna be 1 by c, 1 by c. Well, I could have just copied that one anyway. So 1 by r1 0 to t v1 dt plus 1 by r2, r2 0 to t v2 dt, let's see, plus 1 by r3, plus 1 by r3. I think you see where I'm going with the same thing as the differentiator. I'm just trying to pattern match, just like in the last video. So the thing is, okay, so you have these integrals. First thing, this is just some constant outside. Okay, so if you're considering ratios of r, 1 by r, 1 by r1, 1 by r2, and 1 by r3, well, the ratio of these three is gonna be the same as the ratio of these coefficients right here, right? 1, okay, here you have a 1, here you have 4, here you have 10. So ratio of these, inverse resistances, or these are actually conductances, is gonna be 1 is to 4 is to 10. Okay, but we can can actually also say that the ratio of a resistances r1 is to r2 is to r3, well, these are gonna be the inverses of those coefficients, right? Okay, it's just saying this in another way, these are gonna be the inverses of those coefficients. Okay, so this is 10 inverse. All right, so let's actually find this out. So this is, let's try to simplify this. 1, 0.25, and see, um, 0.1, 0.1. Okay, so if I multiply by 100, if I multiply by 100, what I get is 100, 25, 10. Okay, if you wanted to simplify this, the simplest form would actually be 20 is to 5 is to 2. But anyways, the thing is, we obtained a simple version. Actually, the numbers here are pretty decent, to be honest. What I'm getting at is, again, there's no particular solution for these, any three set of resistors that you pick that satisfies this ratio, they will do, given that they're in appropriate range. So we can just set the values as these, actually, in kilo ohms. That would be the best. So our integrator, okay, we could say, well, first thing, I'll bring out the big eraser. Let's see, bring out the big eraser. So erase this, erase this, erase this, and we had, no, wait, yeah, actually, we are not done yet. I completely slipped my mind, but we didn't find the capacitance. We didn't find the capacitance. That was pretty silly. Let's see. I'll go back. Okay. So the capacitance. Well, we just need to consider one of these coefficients. Okay. So let's see. Um, yeah. So if I pick r1, since I'm picking r1 as 100 kilo ohms, r1 as 100 kilo ohms. So you're gonna have negative. I'm equating the first coefficients there. So negative 1 by c times 1 by r1 100 times 10 to the 3, okay, 100 kiloohms. That's I picked as R1. Should have probably written that. So anyway, so I'll write that. I'll write that. So this is 10 to the 5. It's going to be equal to -1, right? -1. The coefficient here is C is going to be, well, the negative signs cancel out. Negative signs cancel out. If I invert both sides and, well, basically I can actually multiply by C. That should solve it. C is equal to 10 to the -5, okay, farads, okay, 10 to the -5 farads. But I can write this as 10 microfarads, 10 microfarads. Yeah. So C, our capacitance is 10 microfarads. All right. Pretty neat. So I'll write in those values. So capacitance is 10 microfarads. Our resistances, as we pick them, are 100 kiloohms. Um, the one is, R1 is 100 kiloohms, R2 is 25 kiloohms, and R3 is 10 kiloohms. All right. So this is our integrator amplifier circuit that we were trying to find. So this our design problem is solved. Pretty neat. Pretty neat. So that's all the problems that I had to show. Just one last thing, same kind of the same discussion as I had about the differentiator. Is this circuit practical or not? Is this practical? Well, the thing is, fortunately, this has way less flaws than the differentiator. Okay, since we're taking an integral, if you just have your regular signal, some noise here, and then again you continue. The thing is, this noise doesn't really affect the integral that much. Okay, so there's no really bother with that. The voltage, output voltage wouldn't behave too abnormally, and also the integrated circuit doesn't become unstable at higher frequencies. So higher frequencies don't make it go unstable. Not affected by noise, much more usable, or has less flaws than the differentiator. But the way we drew this actually does still have a fatal flaw. That is, we are taking an integral. We're just directly taking the integral of the supply voltage. This circuit, this output voltage, actually it's actually going to be saturated pretty soon. Okay, it's going to reach. Suppose say your the op amp supply. Okay, the op amp supply, which we call known as VCC. Suppose say that's 12 volts. You're probably gonna reach, okay, suppose with any normal supply signal, you're probably gonna reach this pretty soon. Okay, you're probably gonna reach saturation pretty soon if you just use the circuit as is. That's why practically, for real world applications, actually, at the very least, what we have to do is connect another resistance called the shunt resistance, okay, in parallel with the capacitor. And I won't discuss it in this video what happens if you do that, because you need to solve a first order differential equation, so I won't discuss it here. But it does prevent this rapid saturation that happens with the integrator. That's why it makes it, more stable, or actually more usable. So anyways, I'll leave it at that. You can ponder about these things more. So that's the end of this video, and study smart.